And now to the next part on our discussion on wave motion. We have periodic wave. In the previous video, we talked about mechanical wave. The simplest type of mechanical wave is a periodic wave. A periodic wave is sinusoidal in shape. Thus, a periodic wave is also referred to as a sinusoidal wave. As a sinusoidal wave, any sinusoidal function may be used to describe the wave. As such, one example of a periodic wave is the sine wave, wherein the sine function is used to describe the wave function. The sine function is used in the wave's wave function. Wave function is an equation that describes the appearance or shape of the wave as well as the motion of the wave. In addition to that, the wave function describes the effect of the wave on the medium as it travels along the medium. For example, let's say our medium is a line of particles lying on the x-axis. A sine wave will cause the particles of the medium to be disturbed from their initial position, from their undisturbed position. Again, we refer to the undisturbed position of the system as the equilibrium position. So for the particles lying on the x-axis is the equilibrium position. And the wave function will cause the particles to be disturbed from their equilibrium position and take on the shape of the wave passing through the medium. So if we have a sine wave passing through the medium, the particles will be disturbed in such a way that a sine function graph or shape will be formed by the particles of the medium. And this disturbance is, of course, moving from one location to another because a wave is a disturbance propagating from one location to another. The wave function of a sine wave is given by y of xt, y, because if the particles are lying on the x-axis, the disturbance will be along the y-axis. So the disturbance will be along the y-axis. So y of xt is equal to ym sine of kx minus plus omega t plus phi. Ym is the wave amplitude. Wave amplitude is the maximum disturbance that the particles may have from the equilibrium position. Equilibrium position, again, for our system of particles is along the x-axis. So the equilibrium position is y is equal to 0. Wave amplitude, maximum disturbance from the equilibrium position. And the minus plus corresponds to the wave propagation direction. If our wave is moving along the x-axis, as shown in the figure, there are two possible directions that the wave can go. The wave may be moving towards positive x direction, or the wave may be moving towards negative x direction. Use minus sign if the wave is heading in the positive x direction, and plus sign if the wave is heading in the negative x direction. And k is the wave number of the wave. Unit is radians per meter, while omega is angular frequency of the wave. Unit is radians per second. Ym, sine of kx minus plus omega t plus phi, kx minus plus omega t, this quantity is referred to as the phase of the wave, and kx minus plus omega t, the unit is radians. Whereas phi is the phase constant of the wave, unit is radians. Going back to our wave function, y is equal to ym sine of kx minus plus omega t plus phi. If you set x to 0 and t to 0, you have y of 0, 0. Ym sine of 0 minus plus 0 plus phi. Y00 will simply depend on the phase constant phi. Thus, the phase constant determines the value of y00. And note that kx minus plus omega t, the phase, and phi, the phase constant, both have units radians. So they both have a unit of radians. So take note of that. Kx minus plus omega t, unit is radians. Phi is unit of radians. That means the quantity inside the sine function is in radians. So in evaluating the sine function, you must set your calculators to radians. So again, please take note that both the phase and the phase constant are in radians. So you have to set your calculators to radians if you are going to evaluate the sine function inside the wave function. Lambda is referred to as the wavelength, length of one wave. Going back to the previous slide again, you have a sine wave moving from one location to another. Sine wave, sine function. One whole wave is one whole sine function shape. So this sine function is one wave. The length of this is the wavelength. The distance from this point to this point, one whole sine function, that's the wavelength. Length of one wave. If you stand at this point and you measure the time it takes for one wave to pass by you, you are measuring the period of the wave. Time for one wave. And as the name suggests, periodic wave, the period of a periodic wave is constant. On the other hand, if instead of measuring the time, you stand here, again at the same point, instead of measuring the time it takes for one wave to pass you by, you measure the number of waves passing by in 1 second. You are measuring waves per unit time. You are measuring frequency of the wave. Waves per unit time. Unit is per second. It has its own unit. Hertz. Capital H, Z, Hertz. And V is the speed of the wave. How fast is the wave moving from one location to another? You have the wave speed or speed of the wave, V. Now, for a periodic wave, as mentioned, the period is constant. All of the other quantities are also constant. The speed of the wave is constant. As such, you have uniform motion. V is just equal to x over t. V is also equal to frequency of the wave times wavelength, and it's also equal to angular frequency divided by the wave number, omega over k. And k is equal to 2 pi over lambda. K is also constant. Frequency is just the inverse of the period. F is 1 over period. If period is constant, frequency is also constant. Angular frequency is 2 pi frequency or 2 pi over period. Frequency is constant, period is constant, thus angular frequency is also constant. And lastly, the wavelength is also constant. All of the quantities associated with the periodic wave are constant. All of the quantities associated with the periodic wave are constant. Thus, periodic wave is the simplest type of mechanical wave. Another example of a periodic wave is the cosine wave. Wave function is given by y of xt is equal to ym cosine of kx minus omega t plus phi. Pretty much the same equation form as the sine wave function. We simply replace the sine function with the cosine function. So again, cosine function, wave function is given by y of xt is equal to ym cosine of kx minus plus omega t plus phi. Now, it must be noted that for our periodic wave or sinusoidal wave, our default equation, our default wave function is the wave function for the sine wave. Such that if any problem simply mentions that you have a sinusoidal wave or you have a periodic wave, use the equation for the sine function. If the problem specifically mentions cosine wave, that's the only time that you would use the wave function for the cosine wave. When a wave travels through a medium, particles of the medium undergo simple harmonic motion as the wave passes through them. So going back to our figure, say you are looking at this particle and the wave passes through the particle, that particle will undergo simple harmonic motion, will undergo vibratory motion, moving down and up and down, moving back and forth as the wave passes through the particle. Particles of the medium will undergo simple harmonic motion as the wave passes through them. Thus, the particles are moving. When the wave passes through them, the particles will move. We can get the velocity of these particles, what we refer to as the particle velocity. We can get the equation for the and value for the particle velocity using the wave function of the wave. Wave function of the wave is y of xt. The wave function will give you the location or position of the particles of the medium. We refer to y of xt as position function. So it's the wave function. It's also referred to as the position function. And in kinematics, if you know the equation for position, you can easily get the equation for velocity by differentiating the equation, the position equation or the position function, differentiating the position function with respect to time. So Vy, the velocity function, Vy of xt, is equal to dy over dt, the velocity function. Plotting in the exact value of time and x, that will give you the specific value for the particle velocity. So note that in terms of the wave motion, we have two speeds or velocity to speak of. The speed or velocity of the wave as it moves from one location to another, and the velocity of the particles as the wave passes through them. Particle velocity or the velocity function of the particles. And if we differentiate with respect to time the velocity function, we get the acceleration function. Ay of xt is equal to dvy divided by dt. Differentiation of vy with respect to time. For example, let the wave be a sine wave heading in the positive x direction with zero phase constant. For this wave, the wave function is given by y of xt is equal to ym sine of kx minus omega t. Minus heading in the positive x direction. And phi is set to constant, zero phase constant. So we have the wave function y of xt is equal to ym sine of kx minus omega t. This is the position function. By differentiating the position function with respect to time, we get the velocity function, vy of xt. We get the following equation. Negative omega ym cosine of kx minus omega t. The velocity function. Differentiating a second time, we get the acceleration function, ay of xt is equal to negative omega squared ym sine of kx minus omega t. The position function, the velocity function, and the acceleration function for a sine wave heading in the positive x direction with zero phase constant. And by setting the values for x and t, we can get specific values for the particle position, the particle velocity, and the particle acceleration at that position and time. At that position x and at that time t. And that's it for now. That's it for our discussion on the periodic wave. We'll continue our discussion on wave motion in the next video. In the next video, we take a look at a few examples. So again, that's it for now. Thank you for watching.